Okay, good morning, all the students. We'll now move on to our fifth module. That is understanding how to evaluate the hypothesis. Okay, now what is hypothesis? First of all, we have been encountering this term from all last 4 modules, right? What is hypothesis? It is a statement that is made which can be true with respect to some observed data. Okay, so we are framing a statement, we are formulating a statement so that it refers to some set of observed example. Now, when I say in third world countries, the literacy rate is very low, or in third world countries, the life expectancy is very low, means how did I make that statement? How did I frame that hypothesis? I might have done some experiment based on that experiment, based on observed examples, based on observed data, or based on collected data about the third world countries by taking some representative sample from all of those countries, and I have deduced some conclusion. Okay, in third world countries, in most of the third world countries, the literacy is very, very low. Okay, so by taking the help, by observing the examples that are already existing, I perform some experiment, and based on my results, I'll formulate a statement. Okay, or I'll initially make a statement. I just want to prove it by collecting the examples. Okay, that is called as hypothesis. Say if I tell in US, most of the people are ready to elect Biden, say before the elections. Okay, so I made the statement. Now, how I prove that my statement is correct? I try to do some exit poll. I try to do some survey based on social media or questionnaires sent to the participants in the survey, and I collect all the data and show that 80% or 90% of the people in that observed number of in that observed samples are against Trump, and they are for Biden, right? From that, I can prove my hypothesis that I have made, that Biden is getting largest support for becoming the US president. Okay, so I make a statement and I gather the examples, observed, I gather some say data in order to make my statement correct. In order to prove my statement to be correct. Okay, that is called as hypothesis. If you're making any generalized statement about the observed examples, then it is called as your hypothesis. Now, say you go to a manufacturing company, you have to check the performance of the machinery. Now, you observed some deterioration in the performance, means reduction in the performance. Now, you frame a hypothesis. The performance of the plant has reduced. Okay, that is your hypothesis. And how do you prove that? You take instances where you have seen that performance has deteriorated. Okay, sometimes it is working well, but most of the times it is not working well. Now, gather all those instances and provide a support to your hypothesis, claiming that your hypothesis is true. Right? So, hypothesis is a statement made which has to be which has to hold good with respect to some examples, with respect to some observed data. Okay. Now, what is the motivation to behind this? What is the motivation behind evaluating the hypothesis? Why do you need to evaluate the hypothesis? When you make a statement, you have to examine it, you have to prove it. But why to do that? And why is and what is estimating hypothesis accuracy? That we are going to see today. Hypothesis may not be accurate 100%, but up to 98% it may be accurate, up to 95% it may be accurate. There may be some confidence intervals in which you claim that that particular hypothesis is accurate. Confidence interval means you have confidence that most of your data, 95% of the data is in support with your hypothesis. is in support with the statement you have made, and 5% of the data is against your hypothesis, right? So that will prove the accuracy of the hypothesis. Now, how to estimate that hypothesis accuracy? Let us see. Now, empirically means if you want to understand, gain experience from observed data, then it is called as empirical analysis, right? Empirically evaluating the accuracy of hypothesis is fundamental to machine learning. Now, you always gather the data and formulate the hypothesis and show that hypothesis data, how much it is supporting the hypothesis, right? So, empirical evaluation of the accuracy of hypothesis is the basic idea of any machine learning algorithm. You want to prove something and you're gathering data to prove it. That's all. That is the simplest way to understand what is this hypothesis. It is empirical evaluation of the accuracy of hypothesis, and it is fundamental to any machine learning. Now, this module represents an introduction to statistical methods. Now, if you make a statement, whether it is statistically significant or not, understand this term, statistically significant. Now, whenever you're making a statement, you have to prove that it is statistically significant by supplying sufficient number of observed data, sufficient amount of observed data, right? So this module mainly focuses on introduction to statistical methods for estimating hypothesis accuracy, focusing on main 3 questions. What are those questions? First, given the observed accuracy of a hypothesis over a limited sample of data, how well does this estimate its accuracy over additional examples? You know that sample is limited, right? Now, whenever you're studying about third world countries, do you gather each and every possible data point from all the third world countries? Third world countries means where the development is very, very less. Okay, something like African countries, say Sudan, Nigeria, all these are third world countries. Okay, now if you are gathering data about these third world countries, are you going to take each and every data point available? No. You take sample, representative sample. When I'm studying about students in my class, I want to take a representative samples, and normally the representative sample will be 30% of the population, okay, roughly 30% of the population. So whenever I can't make my experiment at a larger scale, I can't gather each and every data points, population data. Now I have to take a representative sample of it. Whenever I'm studying about the students in my class, I have to take representative sample out of it. Means 5 boys, 5 girls, or 10 boys, 10 girls. If I take only 2 girls information and 20 boys information, that is not a representative sample. Okay, so when I take the sample, it should be representative of the population at large. Right? That is why I have to take equal number of male students and female students. My sampling should not be biased. It should not be biased to a specific type of, to a specific category. Okay. So given the observed accuracy of a hypothesis over a limited sample of data, how well does this estimate its accuracy over additional examples? Okay, now your hypothesis is true for this sample that you have collected, but how well does that estimate its accuracy over additional examples, examples that you collect later, or how well does it generalize to new data? That is a question, right? Your sample, your hypothesis is fitting very good to your sample. Now, a new data point comes. Will your hypothesis apply to the new data point with the same amount of accuracy? That is the question. Okay. And second, given that one hypothesis outperforms another over some sample of data, how probable is it that this hypothesis is more accurate in general? Okay, now you have formulated 2 hypotheses, consider. Now, you also observe that one hypothesis is performing better than the other hypothesis. Now, this better performing hypothesis, does it generalize well with the unseen data? That is also a question. Sometimes you have noticed, right, though a complex hypothesis performs without any errors on your data, you better select simpler hypothesis which commits moderate amount of mistakes, right? That you understood from Occam's razor method. Same thing we are talking here also. If there are two hypotheses and one hypothesis is performing better than the other hypothesis, does it generalize well to the news data? Or the other hypothesis which is not performing well is more generalizable? Again, there is an issue, right, to understand. And third one, when data is limited, means you don't have so much data. Sometimes data will be data set contains lakhs of data points, and sometimes data set contains 20 or 30 data points, where it is very critical to gather the training data. Okay, so when data is limited, what is the best way to use this data to both learn a hypothesis and estimate its accuracy? So what is the best way? Whether to split the data set into training set and test set, or do some cross validation so that you divide your training set into some 10 parts, and one part you take it as test set and 9 parts as training set. Again, in the next iteration, take a different part as test set and the remaining 9 parts as the training set. Which is the best way to use the limited data? Which is the best way to use this limited data to both learn a hypothesis and estimate its accuracy also? How do you estimate the accuracy of a hypothesis? Only by seeing how good your model predicts the unseen data or new data point, right? So you have to see what is the best way in order to learn the hypothesis as well as estimate its accuracy also. Now, limited samples of data might misrepresent the general distribution of data. Estimating true accuracy from such samples can be misleading. Sometimes if you have limited data, say I want to study about the students in my class and I take only 6 students data, then I call it as limited sample, because my class contains 60 students and 30%, at least if I don't have the data collected, then it is a limited sample and I can't understand the distribution of data across those sample points. Say if you have some 100 data points or 200 data points, it will be sufficient to understand the distribution, whether the distribution is a normal distribution or whether the distribution is a skewed distribution. That you can understand only if you have more amount of data, right? Say if I have all 60 students data when I want to perform a study about my class, then it is well and good. Otherwise, at least some 50% or at least some 30% data if I have, then it will be easy to study the distribution of data. How many of those data points fall in this range? How many of them fall in this range? How many of them fall in the majority range? Okay, in order to make a study of that, you always require some good amount of sample. So limited samples of data may misrepresent the general distribution of data. You may not have good representation of the data. And it is difficult to estimate true accuracy from such samples. It may be misleading. Now you concentrate only on 6 students in your class and formulate a hypothesis about the 6 students. They may not be a good representative sample, which will mislead your experiment results, which will mislead the statement that you make about the data. Got it? Now, statistical methods together with assumptions. Always remember, whenever you're performing an experiment, always some assumptions are associated with it. And we have been seeing from the module 1, what are the assumptions we have made with respect to various machine learning models. Decision tree, you prefer simpler trees. neural networks, you prefer simple architecture in the neural networks, or you prefer less number of hidden layers. Like that, you have say in finest algorithm and candidate elimination algorithm, you prefer only conjunctive combination of attribute, not disjunctive combination of attributes. Like that, with every machine learning model, you have to associate some assumptions in order to come to a clear endpoint where you complete your experiment. Otherwise, it will be like infinite. You can't come to some stable conclusions. That is why you have to associate assumptions with your experiments. Now, in this statistical methods, together with assumptions about the underlying distribution of the data, sometimes we may assume that data is having normal distribution. Sometimes we may assume that data is having similar variance. Like that, you make some assumptions about the underlying data. Now it allows one to bound the difference between observed accuracy over the sample of available data and the true accuracy over the entire distribution of the data. Means it helps us to limit our study. It helps us to limit the difference between observed data, observed accuracy over the sample of available data. Means say I am observing this accuracy over 30 students. Now that is not too much different when I apply this study to 60 of my students. Okay, so I'm trying to study 50% of the population, and when I'm trying to apply that experiment results to 100% of the population, there should not be any difference in the accuracy, or the difference should be very minimal. Okay, so we have to make some assumptions with the statistical methods in order to allow one to bound the difference between observed accuracy over the sample of available data and the true accuracy over the entire distribution of data. Got it? Sample of available data means, say if I take 30 students data. Over the entire distribution of data means I take 60 students data. Now, if the hypothesis is correct for 30 students data, it should also hold good for 60 students data, 100% of the population. My class having 60 students is my 100% population, my population of study. Now, in that I'm taking 30 students data means that is my sample. Got it? In this class, we have 60 students. Now, among the 60 students, I draw a representative sample, 30 students. Now, this 60 students, we can call it as population, 100% population. And this 30 students, what I have drawn is the sample. Okay, so I'm taking 50% of the population as my sample here. Right? Now, whenever a hypothesis is good, is giving good accuracy, or whenever a statement made is holding good with this number of sample points, now that take that accuracy A1, and if you measure the accuracy when you generalize that particular hypothesis, means whenever you're trying to predict for other 30 students, if there the accuracy is considered as A2, the difference between A1 and A2 should be as minimal as possible. For that, we make some assumptions that the data is normally distributed, or the data is Poisson distributed, or the data is skewed. Like that, lots of assumptions can be made. But now at present, you need not go into depth of what types of distributions you have. But still, if you are interested to understand it properly, you can just Google it. What are the types of distributions of data? You will get Gaussian distribution, this one, Poisson distribution, and lots of other distribution varieties. You can make a study of it. Now, what is the motivation behind evaluating the hypothesis? Why do you need to evaluate your hypothesis? Why do you need to examine your hypothesis in depth? In many cases, it is important to evaluate the performance of learned hypothesis as precisely as possible. Sometimes precision is very much important. Precision means correctness in the accuracy, correctness in the results you get. Okay, so highly precise evaluation is required in many cases. Example, learning effectiveness of different medical treatments. Say you're preparing a database of different effectiveness of different medical treatments for, say, a disease called as cancer. Chemotherapy, allopathy medicines, allopathy treatments effect, or homeopathy effect, or Ayurveda treatment on cancer. You're trying to create a database of learning effectiveness of different medical treatments for a particular disease. Now, evaluating hypothesis is an integral component of many learning methods. Why? Because you should know, in this case, which treatment is better for curing cancer, which treatment is very effective in curing the cancer permanently without recurrence of the cases, okay, without reoccurring of the symptoms again and again. Which treatment is more effective? In order to study that, you have to evaluate the hypothesis you have made. Say you're telling Ayurveda is the best treatment for cancer. In that case, do you have that observed data to support your hypothesis, to give best accuracy? That is very important. Evaluating hypothesis is an integral component. It is like involved, complete. It is completely involved, integral component, complete component of many learning methods. It is a joint component in many learning methods. Now, estimating the accuracy of a hypothesis is relatively straightforward when data is plentiful. Right, you have 1 lakh patients data, or you have 10 million patients data. In that case, you can easily claim that you have a representative sample, because across the Indian population, say if you take 10 million data points, it is a representative sample, right? It may cover all sorts of patients. So in that case, evaluating the accuracy of hypothesis is actually easy when the data is plenty. However, when we must learn a hypothesis and estimate its future accuracy given only a limited set of data, then there are two difficulties. You have limited data. You are not able to gather much data, maybe due to confidentiality concerns. Data is not provided because it is very confidential, or because it is a hindrance to patient privacy. In such cases, if more data is not available, then there are two difficulties in evaluating the hypothesis: bias in the estimate and variance in the estimate. What is bias in the estimate? Your estimate or your result may be biased because the data is very less. It might not have covered sufficient number of patients. Say from the data available, you have more female patients data, but very less number of male patients data. In that case, your estimate will be biased towards female patients, and it doesn't have good representation of male patients. So you may have bias in the estimate. You may have partiality in the estimation that has been done, and variance in the estimate. Variance, if this becomes true, if your hypothesis is true for this small amount of sample, if you take a different sample, again you may get a different accuracy. Again you take third sample, you get a different accuracy. So the variance, the difference in the estimates across the samples will be very high if the data is very less. Okay, so in these cases, evaluating hypothesis has gained very much importance. Okay, now how to estimate the hypothesis accuracy? When evaluating a learned hypothesis, we are most often interested in estimating the accuracy with which it will classify the future instances, right? Whenever future instances are given, what is the accuracy with which it predicts that future instance, or what is the accuracy with which it classifies the future instance? Say these symptoms are given for this. These symptoms are given for a patient, whether he is suffering from this disease or not. That is your classification task. Now you have gathered some 1,000 patient data and you trained your machine learning model in order to classify whether a person has acquired the disease or not. Right? In that case, your machine learning model is set to perform with 95% accuracy. Now, is it performing in the same way with a new data point, with new patient symptoms given? That is of high concern, right? Only then we say, if only if it is predicting well with the new data points also, then we say that your machine learning model is performing very well. Okay. At the same time, we would like to know the probable error in this accuracy estimate. Now, if at all any error is associated with the accuracy estimation, what type of error it is, what is the probable error associated with it, that also should be known. Now let us consider the following setting for the learning problem. Let us start understanding how we can start evaluating the hypothesis. Let us understand first the learning problem, basic learning problem, so that we can proceed with evaluating the hypothesis. There is some space of possible instances X. Now you are very much comfortable with all these notations, right? X represents set of instances. Set of instances means set of training examples, set of observed training examples. Okay. And if you take small x1, that is one training example. X2, that is another training example, like that. There is some space of possible instances, say set of all people, over which various target functions may be defined. Say what would be the target function? People who plan to purchase new skis this year. People may be interested in skiing in their vacation. Now, people who plan to purchase new ski this year, if they are able to predict that, then they can just increase their market or increase the customer experience with them by offering some discount or loyalty points, like that. Okay, so there is some space, and now let us consider there are some training examples provided to us over which a target function has to be learned or defined. Now we assume that different instances in X may be encountered with different frequencies. Okay, we can't say that 50% of the training examples are preferring to ski and 50% of the training examples doesn't want to go for skiing in the vacation, right? Like that, different frequencies are there. We can't see and tell outright that most of the sample points are having this particular label or the other label. We have to assume that different instances in X may be encountered with different frequencies. For this combination of attributes, people are preferring to ski. For this combination of attributes, people doesn't prefer to ski. But a different combination, people are tending to go for not skiing. Like that, there are different combinations. There is no stable combination that for this attributes, people will go for skiing. This attributes, people will not go for skiing. This attribute values, people will not go for skiing. You don't have such stable data. Different combinations are giving different target values, different target labels, yes or no. Now, the learning task will become complex because you have 1 lakh tourist data. In that case, it is difficult to learn, right? A convenient way to model this is to assume that there is some unknown probability distribution D that defines the probability of encountering each instance in X. Now, how to tackle this problem? How to start with this problem? To be comfortable, to start with comfortably, let us assume that there is some probability, but it is unknown. There is some probability distribution D that defines the probability of encountering each instance in X, each training example in X. Okay, probability of encountering this kind of attribute combination is 10%. Probability of encountering this combination of attribute is 50%. And probability of encountering this combination is 80%. Most of the time, if the customers have this combination of attribute values, they are going for skiing, they are preferring skiing. Like that, there are some probabilities associated with training examples. Now, the learning task is to learn the target concept or target function f by considering a hypothesis space H of possible hypotheses. So whenever you want to tackle a learning problem, you assume that a hypothesis space capital H has lots of hypotheses in that. But which is most probable hypothesis? Which is the maximum a posteriori hypothesis? That is your final solution. That is your final statement you make about your data, right? So the learning task is to learn the target function or target concept or target function f by considering a space, hypothesis space H. Now, training examples of the target function f are provided to the learner by a trainer who draws each instance independently. Each instance is drawn independently means drawing this instance doesn't have any effect on drawing the other instance. Then we say that both instances are drawn independently, randomly. Now, pick from a bag of balls having green color balls and red color balls, the draw I make getting a green color ball doesn't affect my second draw I make to get a red color ball or green color ball. In that case, we say both of those draws are independent draws. In that way, training examples of the target function f are provided to the learner by a trainer who draws each instance independently according to the distribution D. According to the underlying distribution D. We do not know what is the distribution, but we are assuming that to be D. And who then forwards the instance small x, that is each training example, referring to each particular training example, along with its correct target value f of x to the learner. Got it? Now we are supplying one training example and its target label to the machine learning model. And we assume that none of the target training examples have dependence on the other training examples. They are all drawn independently. Okay. Now to illustrate, consider learning the target function. Now what is the target function to be learned? For example, people who plan to purchase new skis this year. Now, organization wants to know how many of the people, they wants to know the people who plan to purchase new skis this year. What is the use of that? They can send them some targeted advertisements that if you purchase ski, this would be your discount, or you gain this much cash back, or you gain these many loyalty points. If such kind of targeted advertisements are given, they can hit the customers and make them buy their product. Okay, that is why the target function that has to be learned here is people who plan to purchase new skis this year. If they know that, they can increase their business. Okay, so the target function is to learn about the people who are keen to buy, who are interested to buy skis this year. Given a sample of training data collected by surveying people as they arrive at a skiing resort. Okay, some people are on a vacation and they're going to a skiing resort. Now the company want to estimate how many of them would purchase the new skis. In this case, the instance space X, that is the set of training example X, is the space of all people who might be described by attributes such as their age. What would be the attributes? Age, their occupation, how many times they skied last year. All these parameters are recorded for each customer. Now the distribution D specifies for each person X. X is what? Each training example, right? Each training example is data related to a person. That is why the distribution D specifies for each person X the probability that X will be encountered as the next person arriving at the ski resort. So what is the probability of a person having this kind of attributes arriving at the ski resort? So that they can, the machine learning model can estimate the target label, whether they'll buy the ski or doesn't buy it. Now the target function f, how do you model that? As each of the training instances in the training instance set capital X is mapped to either 0 or 1. If they buy the ski, it is 1, S. They are buying the ski, S. If it is 0, no, they are not preferring to buy the ski. So it is 0, 1. Binary classification, yes or no, default or not, 0 or 1. Do you remember? It is a binary classification problem. The target function classifies each person according to whether or not they plan to purchase the skis. Now, within this general setting, we are interested in the following two questions. Now, you understood the problem. You understood the problem statement, right? Now, what are the two questions we are interested in here? Given a hypothesis H and a data sample containing n examples drawn at random according to the distribution D. You are not taking any outliers. Means you don't take a person who is always at home and want to predict whether he'll buy a ski. Is it a valid training example? No. You are drawing the training examples independently according to a distribution. Means you're seeing among the people that performed skiing last year, from them only you're drawing the sample points, right? That is what we mean by drawn at random according to the distribution D. Okay, you're not taking any outlier point like people who always sit at home. Is a company interested in finding whether a person sitting at home is going to buy a ski? No. You are gathering the sample points from the same distribution of data points. That is, people who are going on a skiing vacation, like that. Okay, so given a hypothesis H and a data sample containing n examples drawn at random independently according to the distribution D. They are according to some agreed upon distribution, okay, underlying distribution. What is the best estimate of the accuracy of H over future instances drawn from the same distribution? Now, from the observed training examples, from the given training examples, you formulated a hypothesis. Now, what is its accuracy with the future instances? That is point number 1. That is question number 1. And what is the probable error in this accuracy estimate? That is question number 2. You have some accuracy estimate. What is the probability of error in it when it has to predict a new data point, when it has to predict an unseen data point? That also have to be known. Now we have to understand error in which is of two types, sample error and true error. What is sample error? To understand these questions, we need to distinguish carefully between two notions of accuracy or error. Accuracy opposite is error, right? Now, whenever you're talking about accuracy, it is that you're talking complement of error. So I can say that error in prediction or accuracy in prediction. You might have heard me saying accuracy in prediction, increase the accuracy in prediction or reduce the error in prediction. Means I'm talking about the same topic, right? That is validity of the hypothesis, validity in the predictions. Okay, so one is the error rate. There are two ideas we have to understand with respect to accuracy of a hypothesis or error made by a hypothesis. One is the error rate of the hypothesis over the sample of data that is available, which is called as sample error. Now, if there is any error, say I say like this, 95% of the patients are recovering, or most of the time the manufacturing plant is misfunctioning. When I'm making a statement, what is the truth in the statement? And is there any small error associated with the statement? okay, that you are interested in. Sample error is the error rate of the hypothesis over the sample of data that is available. Again, take this example. In a class of 60 students, I have drawn a sample of 30 students, and now I made a hypothesis, and it is performing well for 95% of the time, and 5% of the time it is giving error, right? This is called as sample error. Now I test my hypothesis with the larger population. Now I draw a data point from this other 60, other 30. I have drawn a sample of 30 students, but 30 students are left out, right? Now from that 30 students, if I draw a new data point and I want to test my hypothesis, how good is my hypothesis predicting? How good is my model predicting? It is predicting with 95% accuracy again, right? In that case, 5% I am getting again error. So that is called as true error. The error that is associated with the sample is called as sample error, and the error that is associated with the larger population when the model is made to predict unseen data, that is called as the true error. Did you understand, students? Students, did you understand, or you want me to repeat this again?
Understood.
You understood?
Yes, ma'am.
Okay. I'm taking 1 lakh patients data. Among that 1 lakh patients data, actually the patients are larger in number, but I'm taking a sample of 1 lakh patients. Now, I created a model. I designed a model, machine learning model, which will predict well, which is trained on this 1 lakh patients data. And it has some accuracy, say 98% accuracy. Now, that 2% is called as sample error. Now, I'm testing my model with another 10,000 patients data, which is not included in the sample. Now it is giving 95% accuracy. Now this 5% error out of 100, 95% it is giving accuracy, and this 5% error is called as the true error. Got it? Now the other error rate of the hypothesis over entire unknown distribution D of examples is called as true error. Unknown distribution means 1 lakh patients data is known distribution to the model, but 10,000 patients data is unknown distribution to the model. In that case, any error associated with these 10,000 students prediction, any error associated with it, that is called as true error. Okay, the error associated with sample is called as sample error. The error associated with unknown distribution, unseen data, is called as true error. Now the sample error of a hypothesis with respect to some sample S of instances drawn from X is the fraction S that it misclassifies. Got it? See, it is clearly mentioned in the mathematical form. The sample error of a hypothesis with respect to some sample S of instances, say 100 instances, drawn from X, say some 1000 instances, is the fraction of S that it misclassifies. Okay? Say if you have 100 data points. Out of this, it made 95 correct predictions and 5 wrong predictions. Then we say that 95 by 100 is its accuracy and 5 by 100 is its error. That is nothing but 95% is its accuracy and 5% is its error. Okay. So what is the definition here? The sample error denoted by, see the notation. You have to follow this hereafter. When I say error suffix H, error suffix S, H, I refer to sample error. Okay, the sample error denoted by error SH of hypothesis H with respect to target function F and data sample S is, how is it defined? Average of all the differences in the target function and the hypothesis, where N is the number of samples in S, this one, number of samples in S, and the quantity delta f of x and h of x is 1 if f of x is not equal to h of x, means there is some error. When your learned target function is not equal to the target label that is predicted by your hypothesis. Do not get confused. Listen to me carefully. When the label learned by, when the label that is given in your training example, learn target function, is not equal to the label that is predicted by your hypothesis, then it is error, right? So that error, if both are not equal, then error, if the target label and the predicted target label are not equal, then the error is denoted as 1. If both are equal, then there is no error. So it is denoted as 0. Now, refer to this formula once again, representation once again. Error, sample error is defined as, is equivalent to average of all the training example errors when x belongs to the sample data points, sample instances. Okay, dou of what is the original target label f of x and what is the predicted label by using hypothesis h of x. If there is an error, it is 1. If there is no error, it is 0. Now add up all those errors. Say it has made 5 errors. Okay, 1 plus 1 plus 1 plus 1 plus 1. Total 5 predictions have been made as wrong. 5 classifications have been made as wrong. So the average of that will give you the sample error. Then what is true error? How do you represent that? The true error of a hypothesis is the probability that it will misclassify a single randomly drawn instance from the distribution D. Now you take a unseen data point from larger population and you pose that, means you give that new instance to the machine learning model to make it predict the target label. Now, if it misclassifies that, what is the error associated with it? Say you give some 10 data points or some 20 unseen data points or new data points to the machine learning model. Out of that, it is making only 15 correct predictions and 5 wrong predictions out of 20 new data points. In that case, we say that 75% accuracy is seen with the seen in its generalizability. Means it is showing only 75% accuracy with the unseen data and 25% error in the 25% will be the true error in that particular case. You understood this? A model, machine learning model is trained and 20 new data points are given to it to predict. Out of that, 15 data points it predicted correctly and 5 data points it predicted wrong. Now we say that the true error of that particular machine learning model is 25% because it is showing only 75% accuracy. Got it? So the true error, now you understand the definition. The true error denoted by error D of H of hypothesis H with respect to the target function F means target label and distribution D is the probability that H will misclassify an instance drawn at random according to D. So the probability, if the probability of H is more that it will misclassify, the true error will be high. The probability of H misclassification is low, then the true error will be low. So how is it defined? Error, the true error of H is equivalent to, how is it represented? probability of f of x, the target label, not being equal to the label predicted by the hypothesis, the label predicted by the machine learning model. When I am saying machine learning model, it is operating according to a hypothesis, right? That is why we are giving it as h of x for the predicted label. Now, if both are not equal, then some error has occurred in the classification. Now, what is the probability of that error? That is your true error. Here the notation probability x belongs to D denotes the probability is taken over the instance distribution D. It is drawn from a distribution D. It is not entirely drawn from a different world. It is drawn from the same type of distribution, but it is giving some error. In that case, we call it as true error. Now, what we usually wish to know is the true error, error D of H of the hypothesis, because this is the error we can expect when applying the hypothesis to future examples. Correct? This is what I have been telling you. Our sample error is not of interest to us. Whether your data, whether your machine learning model is generalizing well to the unseen data, whether your machine learning model is generalizing well to the larger population, whether your machine learning model is predicting the unseen data correctly or not, that is of interest, and that is called as true error. Because this error we can expect, this is the error actually we expect when applying the hypothesis to the future examples. So we are more interested in true error than in sample error. Got it? All we can measure, however, is the sample error. But is this under our control? Measuring true error is under our control. For this sample, this hypothesis is true. For same, for a different sample drawn from the same distribution, yes, this may be working correctly. This hypothesis is true for this sample also. But can you guarantee that that hypothesis works for the third set of sample with the same accuracy? No, always there is a chance. That is why we are calling it as approximation problem. Approximation means you're estimating, you're guessing something, and guessing is not 100% true. Okay, that is why we are actually interested in true error, but we can measure what is under our control is only the sample's error. We can measure only the sample error. We can't always measure the true error because it may be working very well with some samples at hand, but entirely new sample comes from this, though it is from the same distribution, it may not be predicting with that accuracy. Okay, so though we are interested in true error, we can calculate only sample error. That is why you have to draw representative sample for working with the data. Representative sample will always give lesser sample error as well as lesser true error also. Okay, so all we can measure, however, is the sample error, error S of H of the hypothesis for the data sample S that we happen to have in hand, which we have under our control. Now the main question is, how good an estimate of error D, that is true error, is provided by sample error. Now, how well can you estimate the true error if you know the sample error? That is the main question. Okay, that is how you can evaluate whether your machine learning model is generalizable or not. That is how you evaluate whether your machine learning model is working well with unseen data also, is predicting well with unseen data also. Okay. Okay, time up. I think this concept we can cover in the next class, confidence intervals for discrete valued hypothesis. Any doubts still here, students? New chapter. If you don't understand the starting concepts, it will be difficult for you later. So are the concepts clear, what have been taught today? Any one of you, can you ensure? Okay, because these are entirely new terminologies what we have been using, though they are covered in previous modules, still in the next class I'll go through all these this one error types what we have discussed. I'll go through all these topics once again before going to the next topic, so that you'll feel more comfortable with the nomenclature or the terminology what we are using. Okay, meet you in the next class.